Now I want to show you some concepts on the sample size and the basic idea. And does it work? Yes. And the first point is why should we sample anyway? And then coming to the sampling methods, a little bit about the mathematical background, but I keep it very short. And then the sample size calculation for detection of disease and the prevalence estimation. And that has been shown a little bit by Maria, the influence of sensitivity and specificity on sample size. And to keep you awake, for the whole presentation, I have again a population with 1,000 animals. And we don't know if there are any diseased elements in this population and how many of the animals are healthy. First, I want to know from you if you are working with sampling. So, did you ever planned or performed a surveillance system until now? So I don't need to hide the results. So maybe for those who performed only the surveillance systems, it would be interesting to understand why it is planned in this way. So we have 15 answers at the moment. So it's we have everybody in this group from people who did both to people who have no information about a surveillance system. Okay. So, and the second question is, for those who performed the surveillance already, is how to find out if and how many animals in the population, our virtual population, are diseased. I will switch. So please add your answers, and you can hear the code, see the code 3322248. Okay, it's the same problem.
It doesn't go further.
Yeah, I know. Now it should work. Okay, I can see the first answer. It is screening. Any other ideas? Okay, we have the confirmation retesting. So if you have an unknown population, what would you do? So the main thing is screening, interview, and there is some specificity of the test. Yes, we need the quality of the test. Literature, if the population is unknown, is not helpful often, or it might be very old. Prevalence study is very nice. Population size, we will need the population size to see how many animals we have to test. Okay. So we have different ideas. So there's one idea none of you has mentioned. We can test all the animals in the population. And this is called census. And then we can run a sample survey. So census means I will test all the individuals of a population. And at the end, we know exactly, despite the test quality, how many animals in the population are diseased. And this will give us the best results, but it is very expensive and it is difficult. Maybe some of you performed it within one farm, so testing all animals within this farm population. And then we can run a sample survey. This means that only some of the individuals of a population are investigated, and the distribution of the variables is estimated, and we need to make some assumptions. So this is based on the book of Trustfield. So we need a representative subunit. I come back to this later on. And this one is less expensive. It is easier to carry out. But in the next slides, we will see that it has some side effects. So, and here you can, in general, so if you test all animals, the costs are very high. And if you test only a few animals, the costs are lower, but the inaccuracy is increasing. And if you decide to run a sample survey to find out if the disease is present and how many animals are diseased, please discuss briefly how many animals need to be tested. You don't have to go into details. We come to this calculation later on, and decide which animals have to be tested and what do you need to know in order to perform the sampling. Come back to in contrast to Inge, I have only the free version of Mentimeter, and I have only a limit of 2 slides, so sorry for that. So maybe what do you need to know to determine how many animals need to be tested? I hope it's not closed too, so maybe somebody can test it. And so the code is 8298228. Okay. we have this prevalence is very dominant. And then we have in small the design prevalence, and maybe it's a better wording because we don't know yet the prevalence in the population. Population size, yes. Test sensitivity and specificity is always a good idea. And then I can see here the accepted error and the level of confidence. And I need, yes, susceptible animals. So I need epidemiological background. I need to know how the disease behaves. So if you remember the presentation this morning, it can be very different between different diseases. So it's very important to have at least several of these information. So for me, I would say the population size would be essential, the prevalence, and yes, the confidence level. If you want to run a prevalence survey, we need the accepted error, and the sensitivity and specificity would be very helpful too. Okay. And which animals have to be tested? What do you want to know? Think about different diseases. All the examples this morning with mastitis. Okay, I can see here randomly selected, case definition, yes, and the risk population, age of animals can be helpful in some diseases, and predominantly here is susceptible animals, and you can summarize it and you need information about the disease and the epidemiology of the disease. Okay, coming to the sampling method. So in general, we differentiate between non-probability sampling methods and probability sampling methods. So non-probability sampling methods are convenience sampling. So here, this is from the survey toolbox for livestock diseases. Some nice examples. Convenience sampling means I take the first 5 pigs I can get, and purposive sampling, I test only young pigs, so or piglets here. And probability sampling might be random sampling. So at the beginning, I have to give each individual number, and then I randomly select the number, and I test all the animals within I selected. Systematic sampling might be easier to perform. So you take each 5th animal to test when they are all in a row. Maybe you can write in the chat what is it's always called simple random testing. Is simple random testing really simple? So Tanya has written no. Why isn't it simple, Tanya?
Because you have to have information on all susceptible animals or your risk population, and you have to have access to them.
Yeah.
So that's really not simple.
So for that reason, many people decide to have a systematic sampling, and some, if you give the vet tell the vet, please take samples from different farms, you often get these convenience samples or use animals that can be accessed easily. So Jacinto asked, can we use a mixed approach? Within convenience sample, use random for selecting. Convenience means you select animals you can access easily. And it can be that this is right, but it might be that you have a wrong population tested. One example giving, if you select the animals you can access and you grab animals from a herd, then you will always grab these who cannot walk or cannot run away fast. So maybe you have a subset of diseased animals already. Maybe they have lameness. And then we have stratified and cluster sampling and multi-stage. I will come back later to this. These are more complex sampling strategies. So convenience sampling is really simple. It's not representative, and often it is biased. Purposive sampling, you have a certain selection from population, and you have an information for this subgroup, but you don't have an information for the whole population. This can be used for risk-based surveillance, but then you should, within your subpopulation, you should select the animals randomly. And we discussed this already. Simple random sampling in the field is not really simple. It is representative, and systematic sampling, it is easier to be done than simple random sampling, but you might have a bias if something is happen in your farm. If you have these boxes with pigs and you select one pig of each box, then it can be that for any reason you have a higher bias. Now, coming back to my design population. So we have 1,000 animals and we have a prevalence of 5%. So here it's randomly, I selected 49 animals and they are diseased. Now, in theory, it's quite easy. I can just select some animals and I have a subset. This is my sample. And here from this sample, I grabbed 8 diseased and 92 healthy animals. So here you can see the prevalence is 8%, but in reality, you have seen the prevalence is about 5%. So if you repeat this sampling several times and repeat it more and more, then you will come to better results. And here you can see the influence of the sample size on the prevalence estimation. So I run this sample 1,000 times, and always what I did is I selected different number of animals out of the population, and then I checked how many positives and negatives are in this sample. And with a sample size of 50 animals, you get, in a mean, you get a prevalence of 4.84%, but you can see that the confidence intervals are quite high. If you take 100 animals, the confidence intervals are lower, and you will get the best results and mainly very often the right prevalence if you take a sample of 500 animals. And now you have to find out a compromise between the number of sample size and the precision, the accuracy of your sampling. And here I looked at convenience sampling. So I just grabbed all animals in the top left position. And yeah, by chance here you have only 2 animals diseased out of 82. And you have a estimated, or in your sample, you have a prevalence of 2.38%. So this might be a convenience sampling, and again, it can be right. So even with your convenience sampling, by chance you can be lucky and you have the correct prevalence. To make it more complex, here you have not only the disease status for female and male, and here with the circles you can see females, and with the triangular you can see males, and here you can see the prevalence is equally distributed between both of them. So it's fine to use a random sample of all animals, but if, for example, for any disease I have chosen metritis, only female animals are diseased, then it wouldn't make sense to select male animals. So you would choose a subpopulation of females and select randomly from this subpopulation. To summarize, what I've said now is the representativeness. So census will give you the best results, because if you have a perfect test, then the prevalence in the population is it's the same because you test each animal. Representative sample, the prevalence in the sample is nearly the same as the prevalence in population. Risk-based sampling, the prevalence in your sample is higher than the prevalence in the population because you select animals that might be diseased. As an example, I can tell you that for avian influenza, you just select animals that show clinical signs to detect avian influenza in a farm. And if you have a biased sample, then the prevalence in the sample is not equal to the prevalence in the population. And that's what we want to avoid. Now, a little bit on the mathematical background, sampling and probabilities. And in general, there are 2 options, and I think you all know these examples. So sampling without replacement. So it's, for example, lotto or poker, or a survey. So you avoid testing animals twice. And you have sampling with replacement. For example, if you roll a dice, you always have 6 options. If you have this lotto, if you sample 6 from 49 or whatever, then at the first selection you have the chance 6 from 49, but if you did not select one positive, then it's in the second selection you have your population is decreased to 48 and so on until the longer your sample. So what is the difference? It seems quite similar, but it has an effect that is not very nice. So without replacement, the probabilities for each sample are changing. And what I said before, so selecting a certain number with the first ball out of 49 is 1 divided by 49. For the second ball is 1 of 48, or if there's only one positive in the these 49s, then it's 0 of 48, and so on. In contrast, sampling with replacement, you always have the probability to roll a 6 is always 1 divided by 6. And I don't want to go into the details, but if you try to do the exact formula to calculate the sampling, then you can, in Excel or in R, you can go to a population number of up to 170. Because you have to deal with factorial and nobody can deal with it. It's too complex. With some specific methods in Python, you can go to higher numbers and then you have some estimators. In contrast, sampling with replacement, the calculation is quite easy, and if you have a large population, the difference in the sample size between sampling without replacement and sampling with replacement is marginal, so there's nearly no difference. So in most of these calculations you do, they use simplified methods, binomial calculation with sampling with replacement. And you need to know it because if you use it for large numbers, it's fine. If you use it for small numbers, for small population numbers, that can be an essential difference. Now I want to show you one of the 5 or 6 different equations that are circulating where you can calculate the sample size. And now in the first step, we want the detection of disease. And there's a sample size estimation that was published by Cannon and Rowe. And it's really simple. You have the sample size, you need only the population size. It's N and estimated cases in your population. It's design prevalence or based on design prevalence. And you need to know the confidence level. And then we can do it for our population. We have 1,000 elements multiplied with 0.05, so we have a prevalence of 5% in our population. Then we have our population as 1,000, and so if you calculate it, you come to a sample size of 57, and this can be easily be done in Excel. and you can easily change the confidence level. This is for the detection of disease. So what does that mean? So you sample 57, or you take 57 samples, and then you are sure that when all samples are negative, so with 90% confidence level, you are sure that the prevalence is below 5%. So is this clear for everybody? So if one or more positives in your sample, you can only say that your prevalence is above 5%. If none of the samples is positive, then you can say the prevalence is below 5%. And this is different from the prevalence estimation. Within the prevalence estimation, you want to know a certain prevalence. And for example, you have some information that your prevalence in the population is 30%. Then you put in your design prevalence. Maybe it's better to write your design prevalence. And you have to use an acceptable absolute error or precision. So here, if we choose 30% and plus minus 5% is your precision. And then there is a correction term when the proportion of your sample size divided by the population is smaller than 5%. You can use this one, but at the end, even this is easy to calculate in Excel. On the right low in this table, I show you the student's t-value. So here you have to put in the student's t-value, and it is 1.96 for the 95% confidence interval. Now I calculated the sample size for different confidence levels, and for a large population of 100,000 animals with 5% error and different confidence levels. So, and what is quite interesting here, the sample size is highest for a prevalence, design prevalence of 50%. Do you know why it is? 50% is the highest sample size, always. Explain it with relative and absolute error. So with 50% plus minus 5%, the relative error is 10%. If you have a prevalence of 10% plus minus 10%, the relative error is 50% of your estimated design prevalence. So if you don't have any information about the prevalence in your population, please use 50% as design prevalence. So now coming to the previously we always estimated that we have perfect tests. But now I want to ask you, what is the effect of imperfect tests on sample size and the interpretation of the outcome of the survey? And does sensitivity or specificity have a higher impact on the sample size? As you have all heard the presentation from Maria, it should be easy for you. So and these false positives make a lot of problems, because sometimes it's not easy. It can be because of the tests. For example, if you test for pestivirus and for example, in pigs, they get infected with BVD, they can have a false positive for classical swine fever test, or vice versa. And then it's really hard to find out if it can be in the farm that an animal is really false positive. So it makes you a lot of work. Okay. And the second question is, does sensitivity or specificity have a higher impact on the sample size? All people have listened Maria quite well and say it depends on the prevalence. And yes, it depends on the prevalence, and but in general, if you have a prevalence of 90%, you wouldn't run a survey to find out what is the prevalence in your country. So often you are testing for disease freedom, and then the specificity for low prevalences, the specificity has a bigger influence. So assume we have a test for our disease with a sensitivity of 90% and a specificity of 99%. And just remember, we have still our population with 1,000 animals and a prevalence of 5%, with confidence interval of 95% and a sensitivity and specificity of 1. We calculated a sample size of 57. And now I use this tool from developed from Angus Cameron, and it's very nice. And here you have this population size with the test sensitivity and specificity, and you have 57 a sample size. And first look at the third column. If you have a sensitivity of 90%, you need a sample size of 64 animals. If you have a specificity of 99%, you need a sample size of 124. And you have a cut point number of positives of 3, meaning that only if you have more than 3 positives, you can be sure that the prevalence is above 5%. And if you combine it, the sample size increases more, but here you can see that for low prevalences, the specificity has a much higher influence on the sample size. And it results in these false positive animals. So what I did is I fixed here the sensitivity, and you can see with a different specificity from 83 to 100, you can see that the sample size is going up to, by a population of 1,000, is increasing rapidly. So, and the number of cutoffs is increasing too in a population with 5% prevalence. In contrast, if you keep the specificity at 1 and you decrease the sensitivity to, here I have chosen 70, the sample size is increasing, but not too much. So coming back to the presentation of Maria, if you want to know, or if you want for the test, it is very important to have a very high specificity for the prevalence we want to detect. If you want to detect all animals that are positives, then it is very important to have a high sensitivity. The last point in our presentation is a complex sampling design. And I mentioned it before, you have this stratified sampling. So, and you have strata, means you have different subpopulations. And this is quite useful if the prevalence between strata shows large differences. For example, the number of positives by age or by sex. Then you should test each strata individual. But you need the information for each stratum. So you need a design prevalence for both. For if you change between, it's more cluster sampling. What you mean? It's below. I come to this later, Jacinto. And so stratified is more on different population. And in the best case, you should run a random sample in each stratum. And then you should summarize the results for each stratum separately, and then you can come back to an overall sample size for the whole population. But often it doesn't make sense. It's better to have the prevalence for each stratum. Then you can have a cluster sampling. So in a simple way, you have several clusters, so regional clusters, and all animals in one cluster will be tested. But there are many options. So you can say, okay, I choose different clusters. In Germany, we often do it for federal states, and in each federal state, you calculate the sample size for each federal state by the population in the sample size. And then you can combine stratified and cluster sampling, and this makes this whole sampling design quite complex, and you have to be careful because you have an error on each stage of your sampling design. So these errors will be added or will add sum up, and so you need a correction, and it's called Bonferroni correction, and this increases your sample size essentially. So the last example I can give you from my experience is for a blue tongue disease. We were asked if they are allowed to test more than one animal from each farm, because so the background was there was detection of disease, and they wanted to test 150 animals per district. And if you run a random sampling, in the worst case, you have to drive to 150 farms and test in each farm one animal. And from logistic reason, it was not possible to do that. So they asked us if it is possible to test 10 to 15 animals per farm, and then to test 10 to 15 farms to come to this 150. But then you have an error on the farm level and an error on the animal level. So if they want to test more than one, or if they don't want to run a random survey, they have to put this into account, and the sample size was increased due to this two-stage design. As it is very complex, I just added these tools, these EPI tools, where you can find out how to run the sample, and from the mathematical point of view, it's getting very complex, and you will need a lot of information. You need the number of animals in each stratum and for each cluster, and you need to know what are regional differences and so on. So these sampling designs can be very challenging in designing, in calculation of the sample size, as well as in performing it on the farm level or on this cluster level.